In the far north, where the ground has stayed frozen since long before our species built anything at all, something occasionally works its way to the surface. Not a fossil, not stone, a body. Skin, hair, muscle, a trunk. In some cases, eyelashes still attached. Animals that died tens of thousands of years ago, coming out of a riverbank looking as though they died last winter, because the ground they were buried in has never once thawed. One of them was a calf, roughly a month old. Her body was so complete that researchers could examine the contents of her stomach and identify her last meal, her mother's milk. They could see the fat she had been born with. They could work out how she died, trapped in soft ground, mud in her airways. She had been lying there for over 40,000 years. This is what makes the woolly mammoth different from every other extinct animal on Earth. We do not have to reconstruct it from fragments and educated guesses. We do not have to imagine the soft parts, or invent the colour, or speculate about the coat. We have them. Whole. We know what shade of brown they were. We know what they ate, season by season, in the last months of their lives. We have their hair and their fat and their blood vessels. We have read their complete genetic code. In some cases, we have reconstructed the entire life story of a single individual animal. We know this creature better than we know a great many species that are still alive. This is the complete story of the woolly mammoth, where it came from, how it was built to survive a world that would kill an elephant within a day, how the herds lived, raised their young, and communicated across distances we can't hear, what hunted them, what finally destroyed them, and when the last one actually died, which is far closer to our own time than nearly anyone realizes. And at the end of it, there's a question that isn't historical at all. Because right now, in a laboratory, people are trying to bring this animal back, and they think they are close. Let's start at the beginning, because the mammoth did not begin in the cold. The mammoth family originated in Africa several million years ago. They were not woolly. They were not adapted to ice in any way. They were warm climate animals, close relatives of the elephants, emerging from the same ancestral group and going their own way. And then they spread, out of Africa into Europe and Asia, and eventually across into North America. Over millions of years, the mammoth family split into a series of different species suited to different regions and different climates, and only some of them ever met snow. One of these was an enormous grassland animal, larger than the woolly mammoth would ever be, standing perhaps 4 meters at the shoulder. It lived across the open plains of Eurasia, grazing in a world that was cooling but not yet frozen. That animal is the ancestor of the one we're here to talk about, because as the northern world grew colder, as the great cycle of ice ages tightened its grip, populations living furthest north faced a straightforward choice: adapt, move, or die. Over hundreds of thousands of years, one population adapted, slowly, generation by generation, in the way evolution actually works, not with a leap, but with a long accumulation of small advantages. Slightly thicker hair survived slightly better, slightly smaller ears lost slightly less heat. Slightly more fat carried an animal slightly further into spring. Multiply that by hundreds of thousands of years, and you get a fundamentally different animal. The woolly mammoth emerged somewhere in the region of several 100,000 years ago, in the coldest, driest part of the northern world, and it turned out to be so well suited to that environment that it spread across a colossal range, from the western edge of Europe, across the whole northern belt of Asia, over the land bridge that existed when sea levels were low, and into North America. It became one of the most widespread large land animals on the planet. But it wasn't the only mammoth alive at the time, and this is where the family gets interesting. Further south in North America lived a different species, bigger than the woolly mammoth, less hairy, adapted to milder open country rather than frozen steppe. Where the woolly mammoth was a specialist in extreme cold, this one was a generalist in warmer grassland, and it was the giant of the family. And then there were the strange ones. When sea levels rose and fell during the Ice Age cycles, mammoths sometimes ended up stranded on islands. And islands do something peculiar to large animals. On a small island there is limited food, and there are usually no large predators. Being enormous stops being an advantage and starts being a liability. A big body needs a great deal of food, and there isn't any. So over generations, isolated populations of large animals tend to shrink. Biologists call it island dwarfism, and it has happened repeatedly all over the world to many kinds of animal. It happened to mammoths. On more than one island, populations of these giants gradually became small. Not slightly smaller, dramatically smaller, in the most extreme cases, down to somewhere between 1 and 2 meters at the shoulder. Animals descended from 6-ton giants, now standing about the height of a large pony, still with tusks, still with the mammoth build, wandering an island in miniature. Picture that for a moment. Somewhere in the world, for thousands of years, there were mammoths you could look over the top of. So mammoth is not one animal, it's a family, spanning millions of years and several continents, ranging from giants larger than any elephant alive today down to dwarfs the size of a pony. But the one that captured our imagination, the one we have the bodies of, is the specialist, the one built for the cold. So let's take it apart, piece by piece, and look at how it was actually engineered. Start by correcting the size, because the woolly mammoth has a reputation that is somewhat larger than the animal. A big male stood a little over 3 meters at the shoulder, around 11 feet, and could weigh in the region of 6 tons. Females were noticeably smaller. That is a very large animal by any standard, but it is not a monster beyond all comparison. It was, roughly speaking, in the same range as a large African elephant today. What separated it from an elephant was not scale. It was that essentially every part of its body had been modified against cold. And the clearest way to see that is to look at what was taken away. Look at an African elephant, and the most striking feature is the ears. Enormous, thin, threaded with blood vessels. They are radiators. The animal pumps warm blood through them and fans them to dump heat into the air. Because in a hot climate, overheating is the constant threat. Take that animal north, and those ears become lethal. They would bleed heat continuously, and the thin tissue at the edges would freeze and die. So the mammoth's ears are tiny, not slightly reduced, a fraction of the size, rounded, held close against the skull. From a distance, the head looks almost earless. The tail followed the same logic, short and thick, where an elephant's is long and whip-like. Thin extremities freeze, so the mammoth didn't have any. Now what was added? Under the skin, a layer of fat reaching around 10 centimeters thick in places, an insulating jacket wrapped around the entire body. And over the shoulders, that famous high hump. It isn't a spine deformity, and it isn't a hump of muscle. It was largely a fat store, a fuel tank, filled during the good months, drawn down through the winter when there was little to eat. Then the coat, which was not one layer, but 2. Against the skin, a dense woolly undercoat, fine, tightly packed, trapping a layer of still air against the body. Still air is one of the best insulators there is, which is the same principle behind every winter jacket you have ever owned. Over that, long coarse guard hairs, reaching up to a meter in length along the flanks and hanging down like a skirt. These shed snow, broke the wind and kept the underlayer dry, and that mattered enormously, because wet insulation is worthless. Wet fur conducts heat away from the body instead of holding it in. In that climate, getting soaked and staying soaked is a death sentence, so the mammoth's hair was greasy. Its skin produced oil that coated the strands and repelled water. The animal was in effect waterproofed, we know the colours too, from preserved hair and from genetics. Mammoths came in dark brown, in reddish or ginger tones, and in lighter blonde shades, and the colour of hair recovered from frozen ground can be misleading, because thousands of years in the earth can bleach it. The living animals were likely darker than some of the specimens we recover. But the most remarkable adaptation is one you could never see, because it happens inside the blood. Hemoglobin is the molecule that carries oxygen from your lungs to your tissues. It has a temperature problem. As it cools, it becomes reluctant to let go of the oxygen it's carrying. This is part of why extremities are the first thing to die in extreme cold. blood still arrives, but it won't release its cargo where it's needed. For a large animal in a frozen world, that is a serious constraint. You want to let your legs run cold to conserve core heat, but if you let them run cold, the tissue starves. Researchers recovered the genetic instructions for mammoth hemoglobin, rebuilt that protein in a laboratory, and tested how it behaved. It was different. It released oxygen far more readily at low temperatures than the elephant version does. The mammoth's adaptation to cold went all the way down to the chemistry of its blood. It could run its limbs cold and keep them alive, which meant it could hold its heat where it mattered. That is an astonishing degree of specialization. And it's worth remembering as we go, because specialization is a bargain. It makes you superb in one world and helpless in another. Now the feet, which are quietly one of the most important parts of the animal. Elephants, and almost certainly mammoths, don't walk on their feet the way we do. Inside the foot, the bones are arranged nearly vertically, standing almost on tiptoe, and behind them sits a large pad of fat and fibrous tissue that takes the weight. The result is a foot that acts as a cushion and a snowshoe at once. It spreads several tons of animal across a broad, soft surface, which matters on snow, on soft ground, and on the boggy, uneven terrain of the north. It also makes them quiet, enormous animals moving with very little sound. And that pad does something else. It's exquisitely sensitive to vibration, which brings us to how these animals may have communicated. Elephants produce sound at frequencies below the range of human hearing. Infrasound, deep, slow, powerful rumbles that you would feel in your chest rather than hear with your ears. Low frequencies travel remarkably well. They bend around obstacles and carry across open ground for kilometers. Elephants use this to stay in contact with animals far out of sight, and some of that sound travels through the ground itself, detected through the feet and conducted up through the bones. There is no reason to think the mammoth was different, and every reason to think it was the same, which changes how you should picture this animal. Imagine open frozen grassland under a low sun, a herd spread across it, and running constantly between them, and to other herds far beyond the horizon, a layer of sound you would not be able to hear at all. A continuous, invisible conversation moving through the air and through the frozen ground. The Ice Age steppe was not silent. It was full of sound pitched below our hearing. Now the trunk, because the mammoth's was not quite an elephant's. A trunk is an extraordinary organ, no bone at all, tens of thousands of muscle units, capable of tearing down a branch or picking up something small and delicate. It's a nose, a hand, a hose, a snorkel, and a weapon. The mammoth's trunk had a distinctive tip. Where a modern elephant has finger-like projections for grasping, preserved mammoth trunks show a broad, flattened flap at the end, above a smaller, lower projection. That shape is a scoop. It's suited to gathering low grass in bulk and to pushing snow. It's the difference between an animal that plucks selectively from trees and shrubs and an animal that mows an open grassland. The mammoth's face was, quite literally, shaped by the ground it fed on, which brings us to the tusks, the most famous and most misunderstood feature of this animal. Mammoth tusks were enormous. The largest known run to well over 4 meters, and they had a distinctive form, sweeping forward, curving out, then turning back inward, occasionally crossing near the tips. On an old male, they were vast, curved, and heavy enough that carrying them was a serious commitment of energy. People assumed they were weapons, and there was certainly fighting. Males competed, and tusks were part of it. Some specimens show breaks and heel damage consistent with combat. But the wear tells a different story. Mammoth tusks are worn heavily, and the wear concentrates in particular places, on specific surfaces. That's the pattern of sweeping, side to side, along the ground, over and over for years. And that makes sense, because of the central problem of life on the mammoth steppe. In winter, the grass doesn't vanish. It's still standing, dry and dead and perfectly edible, under a layer of snow. It's food, and it's right there, and it's inaccessible to any animal that can't clear the snow. The mammoth's tusks were snow shovels. The most dramatic feature of the most famous Ice Age animal was, above all, a tool for getting at buried grass. And the tusks did something else, without meaning to. They kept records. The tusk grows continuously through life, layer by layer from the inside, new material laid down in increments, year after year. And those layers preserve a chemical signature of what the animal was eating, what water it was drinking, and the conditions it was living in at that moment. Which means a tusk is a diary. Researchers analysed one male mammoth's tusk, sampling it layer by layer across its entire length, and reconstructed his life from birth to death. They tracked the chemical fingerprints of the places he moved through, and mapped his movements across a vast range. And they found a pattern. For his early years, he moved within a relatively limited area. Then, on reaching adolescence that abruptly changed, his range expanded enormously, and he began covering far greater distances. That is precisely what happens with elephants. Young males, on reaching maturity, leave the herd they were born into. The females stay together for life, the males go. One animal's entire biography, read out of his own tusk, tens of thousands of years after he died. And in the same chemical record, evidence of periodic hormonal surges consistent with the intense aggressive state that adult male elephants enter periodically, which suggests mammoth bulls went through the same thing. So let's assemble the social animal. The strongest evidence points to a structure very like living elephants, herds of related females and their offspring, led by an old matriarch. And her value to the herd is not physical, it's memory. An elephant matriarch carries decades of accumulated knowledge about the landscape, where water is in a drought year, which routes are safe, where the good feeding is in each season, which places killed members of the herd before. In hard years, herds with older matriarchs do better. That knowledge is the difference between survival and starvation. Now apply that to the mammoth steppe, where the landscape changes brutally with the seasons and food in winter must be found under snow. An animal that remembers where the wind scours the snow thin, or where the ground stays productive, keeps her family alive. Mammoth society ran on the memory of its oldest members. The young were a long investment. If mammoths followed the elephant pattern, and everything suggests they did, pregnancy lasted close to 22 months, nearly 2 years to produce one calf. That calf was born large, perhaps around 100 kilograms, and it was born into a herd that would surround it, protect it, and tolerate it. Young elephants nurse for years and remain dependent for years beyond that, learning what to eat and where to go by watching the adults. A mammoth calf faced an additional problem no elephant calf faces. It was born into the cold. It arrived with a coat and a layer of fat already in place. The preserved calves show this clearly, and it needed to grow fast enough to survive the winter that was coming. Adults could live 60 years or more, and what ultimately limited their lifespan was teeth. A mammoth molar was a huge ridged slab, built for grinding tough, gritty grass, and grass is abrasive. It wears teeth down relentlessly. So the animal grew a sequence of molars through life, each one moving forward from the back of the jaw as its predecessor wore out and dropped away. 6 sets, that's the allocation. When the last set wore flat in old age, the animal could no longer process enough food, however much was available. Mammoths, like elephants, could effectively starve to death in a field of grass because they had run out of teeth. Now let's put all that into a year, because the mammoth's life was governed by the seasons more severely than almost any large animal alive today. Summer on the steppe was short, and it was the whole point. The ground thawed at the surface, the grass grew fast in the long daylight, and there was food in genuine abundance. Insects too in clouds. This was the season of eating, 180 kilograms of vegetation a day, laid down as fat over the shoulders and under the skin. Everything the animal would need for the following winter had to be banked now. Autumn was short. The grass cured on the stem, drying in place rather than rotting, which is exactly what made this dry grassland so valuable. It preserved its own hay. The herds fed hard, and the coat thickened. Then winter, which is the test. The temperature dropped far below anything a modern elephant could survive. the daylight shortened until, in the far north, it barely arrived. The wind moved unobstructed across open ground, and the food was still there, underneath, so the herd worked, sweeping snow aside with tusks and trunk, exposing the dry grass beneath, moving on, doing it again. This is why the depth and hardness of the snow mattered more than temperature. Light dry snow is workable. Deep snow, or snow with a hard crust of ice from a thaw and refreeze, is not, and a bad winter of that kind could kill a great many animals with plenty of food a few inches beneath their feet. The matriarch's memory of where the wind scours the ridges bare was, in that moment, the single most valuable thing the herd owned. Then spring, which is not relief, but the most dangerous part of the year. The fat is spent. The animals are at their weakest. The ground thaws and turns to deep, soft mud, and a 6-ton animal on soft ground is in real trouble. Rivers swell with meltwater. A great many of the preserved bodies we recover show signs of exactly this kind of death. Animals trapped in soft ground or mud, unable to free themselves. It was the spring, not the winter, that took them. And these animals were not alone out there. An adult mammoth in good health in a herd was close to untouchable, 6 tons with tusks, surrounded by relatives that would defend it. Very little on earth could take on that. But not every mammoth was an adult in good health. The calves were the target. Ice Age predators included lions larger than any alive today, hunting on open ground rather than in cover. There were wolves, hunting in packs, capable of the patient work of separating a young animal from a group. There were bears of exceptional size, and there was a particular kind of big cat, long-limbed and built for endurance, with flattened blade-like teeth. In one cave, researchers found the remains of an enormous number of juvenile mammoths, together with the remains of these cats, suggesting a predator that specialized in young mammoths and carried them back to a den. So the herd's formation mattered. Adults on the outside, young in the middle. The same arrangement elephants use today when threatened, and for the same reason. The mammoth's defense was not its size alone, it was its family. And then there was the predator that changed everything, because it didn't play by those rules. Humans and mammoths overlapped for tens of thousands of years, and the relationship was more complicated than simple predator and prey. We hunted them, and the evidence is direct. Stone points embedded in bone, butchery marks, sites where animals were killed and processed. But consider the problem from the hunter's side. This is a 6-ton animal with tusks longer than a car, in a herd that will actively defend its young, and your best weapon is a sharpened stone on a wooden shaft. Any straightforward attack ends with dead humans. So it wasn't a straightforward attack. The evidence points to intelligence, selecting isolated, young, old, or injured animals rather than healthy adults. Using terrain, driving animals into bogs, ravines, deep snow, or river crossings, where a heavy body becomes a disadvantage instead of a protection. And using the spear thrower, a simple lever that dramatically increases the force of a thrown spear and, critically, lets it be thrown from a survivable distance. Human beings hunted mammoths by refusing to fight them fairly. And when it worked, the return was extraordinary. Meat in quantities that could sustain a group for a long time if dried or frozen. Fat, which in a cold climate is worth more than lean meat because it delivers the energy needed to stay warm. Hide for shelter and clothing, sinew for cordage and thread, bone and ivory for tools. And then there is the use that says the most about the world these people lived in. Out on open steppe there are no caves and there is almost no wood. If you need shelter from a wind that will kill you, you have to build it, and there is nothing to build with. Except mammoth. Archaeologists have excavated circular dwellings framed from mammoth bone, tusks, jaws, skulls, and long bones, deliberately arranged, interlocked and stacked, then covered with hides and packed against the weather. Some of these structures used the remains of dozens of animals. The largest are enormous, rings of bone many meters across. People lived inside the bodies of the animals they hunted. That was the architecture of the Ice Age. But it wasn't only material. The mammoth is everywhere in Ice Age art. It appears on cave walls, painted by people who had clearly studied it closely. The high shoulder hump, the sloping back, the small ears, the domed head, all rendered accurately by artists who knew the living animal. It was carved into figurines from ivory. It appears again and again across thousands of years and thousands of kilometres, which tells you this animal occupied a place in their minds well beyond food. People crawled deep into caves in the dark, carrying lamps to draw it on a wall. And then, over a few thousand years, they were gone. Across the entire mainland range, Europe, Northern Asia, North America, the woolly mammoth disappeared around the end of the last ice age, roughly 10,000 years ago. An animal that had been abundant across a belt, wrapping most of the way around the northern hemisphere, simply stopped existing. Why is one of the longest-running arguments in this field, and it is not settled. The climate case is strong, and it follows directly from everything we've said about this animal's body. The mammoth was a specialist. It was built for cold, and just as importantly for dry, for a hard, open, productive grassland. When the ice retreated and the world warmed, that grassland did not survive. In the north it became waterlogged tundra, mossy, boggy, and far less productive. Further south, forest closed in. Neither can support 6-ton grazers in large numbers. The mammoth didn't lose a fight. Its world was replaced beneath its feet, and the specialization that had made it magnificent became the thing that trapped it. The hunting case is also strong, and it doesn't require anything dramatic. Go back to the reproduction. 22 months of pregnancy. 1 calf. Years of dependency. Years more before that calf can reproduce in turn. A population like that replaces itself extremely slowly, and it has no capacity to absorb an additional sustained death rate. You do not need mass slaughter. You need only to remove animals slightly faster than they can be replaced. Over centuries, the arithmetic does everything else, and nobody living through it could possibly perceive it happening. Each generation of hunters would simply find the animals a little scarcer than their parents described, and assume their parents had exaggerated. Most researchers now land in the middle. Warming fragmented the grassland, broke a continuous population into isolated pockets, and pushed those pockets into poorer ground. Isolated small populations are fragile. Hunting pressure on a fragile, shrinking population is an entirely different force from hunting pressure on a healthy one. 2 pressures at once, on an animal that could not breed fast enough to recover from either. But here the story does something almost nobody expects. The mammoths did not all die 10,000 years ago. As the ice melted and sea levels rose, water flooded low-lying ground, and in places, high ground became islands. On at least 2 of them, mammoth populations were cut off. Isolated, no humans, and no way to leave. On one, they persisted for thousands of years past the mainland extinction. And on a remote island in the Arctic Ocean, a population of woolly mammoths survived until roughly 4,000 years ago. Take a moment with that number, because it does not sit comfortably in the mind. 4,000 years ago is not prehistory in the way we usually mean the word. The Great Pyramids were completed around 500 years ago, which means that when those pyramids were finished, standing, complete, already monuments, there were still woolly mammoths alive on Earth. They outlasted them. By centuries, mammoths were still breathing, still sweeping snow with their tusks, still raising calves at a time when there were cities, kings, writing, agriculture and metalworking. The animal we file away as impossibly ancient overlapped with recorded human civilization. And nobody knew. There was no way for anyone to know. On an island at the top of the world, unobserved by anyone, the last members of a species that had once ranged across 3 continents were quietly finishing. What ended them is still debated. One idea is genetic. A small isolated population inbreeds. Harmful mutations accumulate and can't be purged, and over many generations the population degrades from within. Genetic studies of the last mammoths did find reduced diversity and accumulated damaging mutations, but more recent analysis has complicated that. Work on a larger set of genomes suggested the population actually stabilised after its initial isolation and remained reasonably steady for thousands of years, which doesn't look like a slow internal collapse. If that's right, the end may have been comparatively abrupt. A run of bad winters, a disease, a shift in the island's vegetation, something arriving that they had no room left to absorb. Either way, at some point around 4,000 years ago, a last woolly mammoth died. An animal that had survived multiple ice ages, the loss of its entire ecosystem, and tens of thousands of years of human hunting, was finished. That was supposed to be the end. It may not be, and the reason goes back to where we started, with those bodies coming out of the frozen ground. Dinar falls apart after death. Over thousands of years, it normally degrades into fragments too short and too damaged to reconstruct. That's why bringing back a dinosaur is not a serious proposition. There is no dinosaur dinar left to work with, anywhere, but cold slows that decay enormously. And mammoths spent their last several thousand years inside a natural freezer. So we have mammoth dinar. Not one perfect intact strand, that doesn't exist, but enough fragments, from enough individuals, that the genome has been sequenced and assembled. We know, gene by gene, what separated a woolly mammoth from its closest living relative. And that relative is startlingly close. The Asian elephant shares something in the region of 99.6% of its genome with the woolly mammoth. The differences are real, and they matter, but they are a small fraction of the whole, which raises the question that a biotechnology company has raised an enormous amount of money to answer if you know the differences. And you can edit dinar. Can you edit an elephant into a mammoth? That's the actual approach. Not cloning. There is no living mammoth cell to clone. And there never will be. Instead, take elephant cells and edit the specific genes responsible for the traits that made a mammoth what it was. The double coat, the fat layer, the small ears, the cold-adapted hemoglobin. Then, grow an embryo from those edited cells and bring it to term. And there has been visible progress. Researchers have already produced laboratory mice carrying mammoth-derived cold adaptation edits, animals with long woolly golden coats and altered fat metabolism. Not mammoths, obviously, but proof that the edits produce the physical results predicted in a living animal. The stated target is a first calf within the next few years, carried by an elephant surrogate through a pregnancy lasting close to 22 months. So, should we expect a mammoth? Here it's worth being careful, because the objections are serious and they aren't merely sentimental. The first is definitional. Editing a set of genes into an Asian elephant does not produce a woolly mammoth. It produces an elephant with mammoth traits, hairy, cold-tolerant, superficially similar, and genetically still overwhelmingly an elephant. Critics argue the honest description isn't de-extinction at all, but the creation of a new engineered animal that resembles a lost one. The second concerns the elephants themselves. Asian elephants are endangered. The process needs their eggs, and a surrogate mother carrying a nearly 2-year pregnancy with an engineered calf. Many biologists question whether that's a defensible use of a threatened species, and whether the resources involved would save more animals if spent on the elephants that are still here. The third is about the animal that would result, and it goes back to everything we know about how these creatures actually lived. A mammoth was not just a body. It was a member of a herd, born into a family, raised by a matriarch, taught over years what to eat, where to go, how to find grass under snow, how to read a landscape. Its survival depended on knowledge that was not in its genes. It was in the memory of the animals around it. A calf born now would have none of that. No herd of its own kind, no matriarch, nothing to imitate. It would be a member of a social species with no society, and the closest thing to a parent available to it would be an elephant of a different species entirely. And underneath all of it is a question no laboratory can answer. The world this animal was built for is gone. The dry, cold, productive grassland it grazed does not exist anywhere on Earth. Even a perfect mammoth would be an animal without a home, unless we chose to try rebuilding an entire ecosystem around it, which is a far larger and stranger ambition than making the animal. So come back to the beginning. A body in frozen ground, a calf, a month old, tens of thousands of years dead, with her eyelashes intact and her mother's milk still in her stomach. That's the peculiar position the woolly mammoth holds. It is extinct, and it is the least extinct animal we have. We have its body, its colour, its diet, its blood chemistry, its complete genetic code. We have the life story of individual animals written into their tusks year by year. We have portraits of it made by people who watched it alive and thought it was worth the trouble of drawing in the dark. We know this creature the way you know a living species, and more of them are surfacing. As frozen ground thaws, bodies that have been sealed in the earth since before anyone built anything are appearing in eroding riverbanks across the north. Animals that have been waiting, intact, for longer than our entire recorded history. There is something fitting about that. The mammoth spent its whole existence adapted to cold, shaped by it in every part of its body, right down to its blood. And when the cold finally retreated and took its world with it, the last of that frozen ground kept the animal, held it, unchanged, and is now handing it back to us one body at a time. Whether we use it to try to build a new one is a question we'll have to answer soon. Because for the first time since a small herd died out on an island at the top of the world, 4,000 years ago, the ending of this story is no longer settled.